Hello, and welcome everyone to our webinar at the Hanover Fair after event webinar. So indeed, with many of you, we had already met at the Hanover Fair, but for anyone who has joined from our LinkedIn, welcome to you as well. So my name is Jukka Knuten, and I'm the head of marketing at Quanscient. And along with me here today is our team lead of application engineering team, Dr. Abhishek Deshmukh, who was also present at Hanover. Just as a quick note, this session is being recorded, and all the registrants will receive the timestamp recording and executive summary PDF, whether you registered at our booth at the Hanover Fair or afterwards on LinkedIn. So let's jump into our topic of today, which is Quanscient All-Solve. So basically, what this webinar is all about is to see what Quanscient is and to explore it a bit more deeply than we perhaps had time at the fair. So we're going to look at the just introduction. We're going to look at the key features, key benefits from both the business and technical side. And also we're going to have a couple of live demonstrations from Dr. Deshmukh, showcasing how it actually looks like to set up these simulations, how it is to actually start and run these simulations, and also analyze the results. Afterwards, we're going to have a Q&A session where you can ask any questions from either myself or Dr. Deshmukh, and we'll conclude on a few words. So, about Quanscient. So we were founded in 2021, and we are headquartered here in Tampere, Finland. Currently, we're at 26 employees strong, rapidly growing, and that includes 12 different nationalities. And yes, there are tens of thousands of cores active in the cloud and thousands simulations running weekly. Now, here are the problems that basically Quanscient All-Solve was built to fix. So in a nutshell, the current simulation tools are a bottleneck in engineering. According to a report by ANS, they found that 78% of engineers need to reduce complexity of their simulations due to the lack of computational capacity. Now, 96% of engineering decision makers said that reducing time, risk, and cost is the most valuable thing in their R&D, and 81% of the respondents said that of engineering decision makers said that the flexible software licenses is important to increase simulation capabilities. And as said, these 3 points are pretty much what these problems are what Quanscient also was built to fix. And how do we solve these? In short, the answer is cloud computing. So when it comes to the need to reduce complexity, it is exactly because of the computational capacity. So the computational capacity with the current tools is often limited. And what that means is that there are exactly the need to reduce the complexity of the solutions, or rather the models, which results in less accurate results, or then just very, very slow simulations, or at worst, both. So what cloud computing, and especially our cloud computing algorithms, allow our customers to do is to increase the complexity and decrease the runtime from literally days to coffee breaks. We like to say that you can run 10 times more accurate simulations in a tenth of the time. What else does the cloud scaling make you do or allow you to do is simply more experiments and therefore less prototypes. So you can just run more simulations at a much more larger scale. You can run hundreds of simulations at the same time, which allows you to do optimization tasks, run Monte Carlo simulations, and perform any sort of parametric sweeps. Further on, you can do automated workflows to APIs, which we are actually rolling out in the next couple of months, and the sheer amount of data that is gathered through those can be fed to an AI algorithm or AI uh, neural network, which can be used for AI assisted design. And later on, there's of course the quantum promise, since as many of you might not know, we have a sort of a quantum branch at Quanscient doing research in quantum algorithms. So basically, how to harness the immense computational capacity of quantum computers in these same multiphysics simulations. But as said, that is in the future. But if you're interested in this, you can read more at quanscient.com/quantum. So how does this work? So what allows for the scaling? That basically is exactly the domain decomposition method and the algorithms that our CEO, Dr. Alexander Halbach, has written that allows our algorithms to take advantage of this cloud scaling. So basically, the current standard is either this single CPU multithreading, which allows for speed of, let's say, 4 to 8%, or the state of the art multi CPU with a direct solver, which can allow for 8 to 32 times speedups. But in both of these, the amount of random access memory, so RAM, becomes a bottleneck, and also the algorithms themselves that are in the legacy software, they are basically not equipped to take advantage of the cloud. So no matter how much CPUs you throw at them, they won't scale linearly. Now, with R solver, which utilizes the domain decomposition method, it basically dissects the problem into small parts and solves each of them on individual machines. So basically, instead of solving a massive matrix, it solves the mesh into smaller matrices that are solved on individual computers. What that allows us to do is, or our customers too, is to truly scale linearly to hundreds and hundreds of CPUs. So we can look at an example to see what that looks like in business perspectives, or from the business perspective. For example, this is a case study from one of our customers where they, with their previous software, they were facing a 3-week simulation runtime. So this was 3D electromagnetics. So they were waiting just 3 weeks for their simulations to run, and their accuracy in the results was 10% of their measurement data. So bottom line here is it is very slow and very cumbersome, and you need to build more prototypes to truly validate the results, since you can't really trust them. Now with Quanscient and the aforementioned domain decomposition method, they were able to reduce their runtime to 8 hours. So from 3 weeks to 8 hours, and the accuracy was increased from 10% to 3%. And what this again allows to do is to iterate more rapidly. So instead of waiting for weeks, the simulation basically runs overnight. So yeah, weeks saved in every simulation cycle, more trustworthy design decisions based on more accurate simulation data, and essentially reduce risk, time, and money in R&D and building prototypes. Here is another example from superconductors. Here's a full-scale nuclear stellarator simulation, also 3D magnetics, with 317 million unknowns, which was solved using 500 cores in just 15 minutes. We actually have a full webinar where we cover the superconductor stuff. So if you're interested in that, you can find it on our website under events. Here's another example on acoustics. So this is a 360 million unknown problem that was solved in 20 minutes using 1,000 cores. By the way, we also have an acoustics webinar. So if you're more interested in the specifics of acoustics, again, quanscient.com/events, you can find our acoustics webinar. Finally, I'd like to show a video about a quantum Hanger resonator where we solved a sort of a demo of the parallel sweeps. So basically the possibilities that come from the ability to literally solve hundreds of simulations at the same time if you want, since the licenses are not an issue and the computational capacity is not an issue. So if we can get the video rolling, I'd like to show how that looks like. So there we go. So indeed, here is a quantum resonator used in hardware or quantum hardware with electromagnetic waves, and we wanted to find out the S parameters with different frequencies. So there was a frequency sweep performed from 25 gigahertz to 30 gigahertz with 49 different time steps. Again, everything purely solved in the browser, no downloads required. And as you can see, the simulation were started just like that. You can inspect each of the individual jobs. You can do live plotting to see the different S parameters, different frequencies, and looks like there you have it. All of the results from all of the 49 different runs. You can inspect the logs once again to see that, these 49 simulations were in total solved in just 27 seconds. And as said, with 600,000 degrees of freedom per simulation, that was 27 million degrees of freedom solved in less than 30 seconds. So 49 simulations in parallel, just like that. So that is one of the big things that you can do, since with Quanscient also computational capacity is not a bottleneck. Neither are the number of licenses you have. All right. So as a quick summary of the key features, cloud scaling, that was pretty much covered. So practically unlimited number of computational power and RAM on any device. Runtime from days to coffee breaks, and practically unlimited number of parallel simulations. As said, no user limits, so there are basically an unlimited number of users with every plan. So when an organization purchases computing power, each of the people from the organization can join the platform. They can view projects, they can start running projects, and only when the models are running, when the simulations are running, any money is basically spent. And also, there's no hardware requirements. So there's no need to buy expensive computers, expensive workstations, or invest in any clusters or maintenance of clusters, or even electricity bills for these clusters, since all of the hardware and maintenance of the hardware is included in the packages that you buy. And yes, real-time collaboration, as it is a browser-based tool, is quite literally as easy as sharing a link. Now, one thing that our users like quite a lot is the Python scripting interface. So basically, there is a automatically generated Python script that defines the entire simulation. So whether you want to add some physics our GUI doesn't support, you can do it right there. Or if you want to tweak anything, is in a very readable form. So if you're in any way competent with Python, you can basically do anything you want, and everything is fully customizable. Again, directly in the GUI. As said, user-based pricing. So it is a very cost-efficient tool for both organizations who are solving a limited number of simulations, so not a lot, also for organizations who are running massive amounts of simulations. So both startups and tech conglomerates are users of ours. And finally, the support and materials. So we have the support directly in the tool. It is just a few clicks and the message is already sent. We also have tutorial videos, user guides, and documentations already existing and improving basically and multiplying almost on a weekly scale. So that's pretty much it from the sort of theory perspective when it comes to these benefits of the tool. So now I'd like to pass the mic to Dr. Deshmukh to see how it actually looks like to solve these simulations, to set up these simulations, to analyze the results, and maybe we'll also see a peek of the Python scripting interface. So go ahead, Abhishek.
Yeah, thanks, Yukka. Nice summary there on the cloud benefits. For this webinar, we will have a look at a demo. I chose here a Joule heating, so example of Joule heating, which relatively mostly people know. So you might have seen these coils in your toaster or in the hot plates, electric hot plates, where the heat is generated by electric current flowing through these coils, and this is exactly the Joule heating effect. and we'll see in this webinar how to set this problem up in the GUI, and look at different types of analysis that we can do, and analyze the results. So in this case, so let's if we have a DC current passing through the coil, so mainly the constant current flow, usually the power output of this is given by current square times the resistance. So this is the for the DC power, and if you have AC current flowing through this is basically the current is the RMS current that is taken as the let's say for calculation of the power. And this is important. You will see where it comes in handy, and why this is um, and when we want to simulate such a problem in 3D, if you have some kind of core element, you want to see the heating, you or we in the Quanscient, we solve differential equations, so mainly partial differential equation, as you see for the temperature. In this case, the heating source is calculated by from the electric current flowing. So this is given the current density J dot product with electric field E, and that's what we solve here. So let's move to the demo directly. Let's look at the geometry. For here I already imported the geometry. Like any other software, we have a workflow where you have model, properties, physics, and simulation. So we start with the model, which is the geometric model that you can either build in the environment, or you can also import, like I did here. So I imported a step file which consists of this heating element. Basically, I did some operations, so creating some additional geometries, simple shapes, and uh, some simple operations, Boolean operations, like splitting the domain and removing the unnecessary volumes. And after that, I end up with this geometry where I have three volumes, all kind of six faced blocks. And this is the reason why I did this is because I wanted to use a structured meshing, which is also possible with AllSolve for relatively simple geometries like this. So we can actually create um, a nicely structured mesh. I can show you a preview of this. So these kind of hexahedral elements can be created for relatively simple geometries. That is to highlight the feature. And um, yeah, let's not move into that, but I just want to briefly show how this is set up. You can select a volume, you can add a structured entity. It can be any of these geometric entities. In this case, I added a volume, and I can then simply uh, click on the input box, and I can see the edges that are highlighted, and these are the edges where you will have 10 segments. Then the next set of edges which are parallel, and they should have equal segments. That's why we split it into only let's say three axes. And yeah, you can see that there will be three segments here and three segments on the other. And this is exactly what you also see in the mesh. So once we have all the geometry and mesh, I come back to the model. uh, we can go on to setting up properties. So let's say we add a material. So we have predefined materials in the library, and we are constantly adding new materials. But in case you don't find it, you can also create your own material. So we have ability to uh, add new material which will be specific to this simulation. In this case, let's choose copper. uh, the reason I choose copper is because I want to have fast heating and cooling cycles. And let's add the volume. So you can add the volumes, this which should be assigned copper as the property, material properties. And yeah, so once we have the properties defined, we can move to physics tab. Let's add the, so we had that's the all the list of physics that are available in the GUI, but that's not the only list. You can pretty much do anything in the Python script, if not available in this list of physics. So let's add current flow. uh, we don't need to choose. If we don't choose the volumes, it default is to the whole geometry, so that this physics will apply to whole of the geometry. Then we will have to add some constraints, so some potential on this surface. So I will fix the potential at this surface to 0. Then I will add a driving current. So in this case I use the lumped parameters or lumped ports on this face, and I want to drive uh, with current. So there is also possibility of driving the circuit, or driving the or applying the boundary conditions through a circuit coupling if you need, and also voltage. In this case, let's say add 1 amperes. Then let's add the thermal, uh, so heat solid, which will be um the heating of this element due to current flow. Again, here you don't need to select the geometry if all of the domain needs to be applied with heat solid as the physics. Let's add the some constraint here again. So we want to hold the surfaces, so this leads to the reference temperature. So this is the, keep in mind that this is the reference temperature, not the absolute one. So anything, so you can imagine reference temperature as the room temperature, and this is the increment or decrement over that reference temperature. And last thing that we need to add is coupling of the current flow and heat solid. So there's this Joule heating coupling, and in this case you have to select which volumes this Joule heating should be applied, and there can be less volumes where you, so in this case I will use all of the volumes, but there could be sometimes you just want to see the effect on one part of the let's say geometry. And that's all you need to set up. Then we can move on to simulations menu. We have already created the mesh. There are also default settings available if you would like, and that would create tetrahedral mesh in case of 3D. Um there's also several controls on the um, let's say size of the meshing. You can also define region based size. For example, you can choose a volume, so you would then select one volume and assign the maximum size of elements that you would like to have there. In this case I already showed that I chose structured meshing, so I don't need to do this. We have the mesh ready. Let's add a simulation there. So in this case, let's choose DC, uh, DC current. So I will name this simulation as DC. I chose the steady state analysis, um, and basically different node types that are available. So in here you can select different kinds of machine ranging from 1 CPU to 32 CPU and up to 512 GB of RAM. And this is one machine that you can select, and you can then define as many of these machines that you need. And that's how this will be uh, it will be possible to run, let's say, multiple of these simulations. In this case I would choose fast start, which starts instantly. Then I need to set the mesh here. And before we look at the script, let's add some output. So we would like to take a look at temperature field once the simulation is finished, and I would like to monitor some constant value somewhere in the domain. Let's say maximum temperature in the domain in, so this would be not the absolute one, but the deviation from the absolute temperature. And I can easily add this by computing the max value as the output. And you can see, if you hover on this function, you can see the usage or the documentation of the function. So it needs three arguments. First is region, then the expression, and the refinement. So in this case, region, we'll select the Joule heating target, so that selects the all the volumes that are um, that will have this effect. We'll choose temperature as the expression, and refinement, that's for the accuracy of the calculations. And that's all. And as Yuka mentioned, you get this auto generated script. So all the settings that we did in the GUI, they they are reflected in this Python script, and it's really a compact script, 70 lines, and you can see where the things are implemented. For example, this is the block to load the mesh. This is to define the fields, so potential field, temperature field, some derived fields like current density and electric field that we need for calculation of the um, source, heating source. And this is where you have this equations that you can see what will be used in the simulation. These are literally the weak form of the equations in finite element sense, and the same for the heat solid. And as you mentioned, you can also add or tweak this script. So for that you have to activate the script mode, and then you can start adding any new formulation, just like following the syntax and so on. In this case I won't need to do that because this is a simple enough case. And let's run this case. And you can take, once we hit the start button, because it was not many number of drops, it runs instantly within a second. And we can take a look at visual, which we can take a look at the field that output. We had this temperature field as the output, and we can take a look at the 3D field after the simulation has been finished. And you can see that maximum, so this is the range of the temperature in this domain, and max temperature is about 86 millikelvin. And it can be also seen that the max is about at the end of this heating element. And we also had this max temperature as output, which can be looked at in the summary. You can see max temperature. So once you want a single value as the output, you can have a look at this. And yeah, that's the DC simulation. So that was one simulation. And we can also set up easily sweeps. So for that we have to first define the sweeping parameters. So in this case, let's choose current as the sweeping parameter, current in amperes. Just give some value here. We go back to the physics where we have been driving the current, and I need to change this to shared expression, so that the parameter will be then replaced later in the sweeps. Then moving to simulations tab, here the inputs, you can see the shared expression already appears in the sweeps. You can select here, and this is the nice function. I can go to up to 10 amperes, so from starting from 1 ampere to 10 amperes, and with 10 steps. We can also do maybe 40 steps. And yeah, let's hit the restart. And you can already, when we go to plotting, and once this is already finished or starting, you can already see the input current. So on x-axis the current, and the max temperature on the y-axis. And you can see that as the current increases, the max temperature increases quadratically. And if you remember from the slides, we already had this relation of power with square of the current, and that also is reflected here. That was the steady state analysis. For AC current, we have to do transient analysis, and this is what I will do. I copied the simulation, so it instantly creates a copy of my simulation. I can change the name. I choose the transient analysis, time stepping algorithm, start time and end time, and with some time step. And yeah, that's all. And we can change the current sweep to, let's say, we don't need the sweep here. For AC, we need to define the frequency. So let's define a shared expression frequency of the AC current. So this will be in hertz. I provide a single value here, and then later I also need to define the current. So we'll use current as the amplitude, and then the signal, AC signal, as sine of 2 pi frequency times temp times time. So that's how you can create the alternating signal. And once we do that, we can create a frequency sweep for for this AC simulation, starting from, let's say, 100 hertz to 400 hertz in steps of 4. Then can start the simulation, and we can already look at the plots, and this is the live plotting feature, and we can see for different frequencies starting from 100 to 200, 300 and 400, you can see how the max temperature evolves with time. And for lower frequencies, the time to hit, so there is enough time to heat up the element and enough time to cool down. So that's why you see the large temperature swing here. And as the element hits starts hitting the steady state temperature, as the time evolves, you can see that there is a oscillation about, uh, let's say, some constant um, temperature, constant maximum temperature. And this is about half of the half of the maximum temperature that we had in the steady state. And that's also because in this case we have the RMS current, which for the sine wave is square root, so the the amplitude divided by square root of 2. And because we have square of the current, we have the amplitude divided by 2, and this is exactly what you see, the constant maximum temperature about 0.43 or 43 millikelvins. And for different frequencies, the swing around this constant temperature is different. And for high frequencies, obviously there is not enough time to heat and cool, and that's why the swing is a bit smaller. And yeah, so that's the transient simulation. And uh, for, as you can see, for transient simulation we have to wait until the element is hitting steady state. But for some cases you would like to have you are just interested into steady state frequency response. So for this we have um, nice method. So harmonic balance method, there was a webinar um, on dedicated to harmonic balance, which you can find on our webinars uh, uh, yeah, page. And in this case I would choose multi-harmonic as my simulation analysis frequency. I'll choose um, the harmonics 3, 4, 5, and yeah, and that's all I need. I need to change the output here because this is harmonic simulation, and the output would be in terms of harmonic coefficients, not the absolute temperature. And also for the max temperature I need to define max value of um, these coefficients. And in this case I would choose absolute of harmonic of temperature at refinement. And then I would copy this to speed up the process. I'll need 5 of these custom values, custom outputs, and then I can start editing the second harmonic, third harmonic, and fourth one, and the last is fifth. And I also need to rename them T2, T3, max T3, and T4, and the final T5. And in this case we can do a lot more. So starting from frequency 1 to 400, about 40 simulations, and they would run instantly. And we can look at the frequency response in that case. So that's the frequency as the x-axis, and we can take a look at 5 harmonic coefficients. This is not the temperature but the coefficient or amplitudes in the harmonic sense. And you can see the first constant part. So this is the, I can hide the others to highlight the constant part. So this is the constant maximum temperature, that is about 43 millikelvin, which is also we saw in transient simulations. And the second harmonic is 0. That's the harmonic at the fundamental frequency, and this is 0 because uh, the the power scales with the square of or square of the current. That means the harmonic coefficients that will appear will be at the frequency double the fundamental frequency, and 2 and 3 harmonics are at fundamental frequency, and that's why they are 0 in this case. As soon as I add the harmonic at twice the fundamental frequency, so the sine coefficient and the cosine, you can see these are the contributions from these harmonics at the twice the fundamental frequency. And as the frequency goes on increasing, the amplitude goes on decreasing. This is also what we saw in the transient simulations. For high frequencies, the swing about the constant temperature is smaller. And yeah, that's the harmonic balance. And with this, I think the demo will be, so I showed 3 types of analysis in this demo for the Joule heating. And yeah, we have another example where you can benefit from, let's say, sweeps and large amount of simulations. So here the ultrasound sensors, we have quite the list of physics that was used in this case. There is a MEMS speaker at the bottom which is emitting the sound waves. In this case we use all electrostatics, so there is parallel plates moving, so moving mesh, solid mechanics, compressible flow. And the rest of the big domain we have just acoustics, so to save some computational cost there. So you can couple all kinds of physics. There is also perfectly matched layer at the end of this domain to absorb the sound waves, and you can run such simulations. So in this case I ran 66 simulations, all done within 30 seconds, and I could sweep about the frequency and voltage at the same time, and I could get this map of the sound pressure levels at some location in the domain. And yeah, this kind of large scale um, parametric sweeps can be easily and performed with all solve. And yeah, you can optimize your product. I think with this we can go to the Q&A session, Yuka. um,
Indeed. Thank you, Abhishek, for your demonstrations. Since we are fairly limited on time, since we have just 4 minutes, I could maybe quickly either ask or answer one of the or a couple of the answers or questions that we got beforehand. So one question that we get also a lot, which is a very natural question, is on the security of the cloud. So that is a concern for many. And for that, what we can say is that, well, for one, these big companies that actually host these cloud services or the cloud infrastructure, for example, in our case, that would be AWS, they spend approximately $1.6 billion per year on their security or security alone. And what that basically allows them to do is to host the world top tier infrastructure, have all the security in place that make it as secure as possible. They can employ the security professionals and undergo rigorous exams, tests, and audits just to make sure that their sort of infrastructure is secure. And as said, as we are using AWS, which invests heavily in their security, we ourselves are also SOC 2 certified and working towards the ISO certificate right now. But point is, what we can say is that as opposed to the popular belief of the let's say weak security of the cloud, it is quite literally the opposite. So in many cases, trusting these big cloud providers is in many cases more secure than holding all the data on within your own premises. Uh, Another question that we usually get, or that is also very common, is for one is on the machines. So basically, when you solve these simulations, as you saw, you have the option to choose on how many cores you basically want to solve it on. So Abhishek, what would you say on that? If someone is concerned on what machine should they use, or what would you say?
I would say first run one time step. If you're running, let's say, transient simulation, check the degrees of freedom that you have in the simulation, and we have a roughly a thumb rule of using 100 to 200,000 degrees of freedom per core. So if you have, for example, 200,000 degrees of freedom, then you should use the smallest machine, that is one CPU, 16 GB, and you can scale with that thumb rule as many machines as you want. And it is recommended to use the smallest machine and use many of them. That is, and only go into bigger machines if you are running out of the memory.
Right on. Uh, that's pretty much, unfortunately, it for this Q&A session. I know you guys have more questions. You can type them into the chat anyways. We'll answer them there. You can send them to LinkedIn personally on myself. You can send them to Abhishek. You can send them to our email. But that pretty much concludes this session. There's just one last sort of summary that where I'd like to put together at this point. Thanks for Abhishek. Thanks for joining. So in conclusion, the sort of key takeaways that I want to leave you with is that for one, Quanscient also is a cloud-based multiphysics simulation software. Is if you got nothing else, I hope this is what you know so far. But most importantly, that through our proprietary algorithms that employ the domain decomposition method, our customers can take the full advantage of cloud computing and cloud scaling in multiphysics simulations. What that means in practice is that they can run simulation at a volume that is infeasible with current tools, which allows for larger throughput, more design of experience, and faster optimizations of design. And what this then results in is, in essence, more reliable designs, decreasing time, money, and risk in high technology R&D. I would like to leave you with a question, with sort of a hypothetical question, that if you had no hardware limitations on your simulations, you had no license limitation on your simulations, you could run as complex simulations as you'd like, and you could run them at a scale that you would like. How would that change your simulation processes or R&D processes as a whole if you had zero hardware comments? That is one of the questions I sort of want to leave you with. And if you come to the conclusion that indeed would help you, or that you face the problems that we mentioned in the very beginning that seem to be very common in the industry, I encourage you to learn more. You can read more on our website, which is linked right here, also quanscient.com, and you can feel free to book a demo right then, there and then. You can directly schedule a time with Mr. Nicolas Stra, and if you're not already following us on LinkedIn, I highly recommend you do so. We're quite active there and have a large community of simulation experts. With that being said, we're already 2 minutes after our planned time, so I'll end it for today. Thank you a lot for joining us today, and I wish you a happy rest of the day. Bye bye.